back away from the Earth, and we will get a good view of our neighbor, the moon. So this really thin orbit line right here, it's a little faint, hard to see, but that is the orbit of our moon, and the moon is right over there. So this is about 238,000 miles from the Earth to the moon, and that's the farthest that humans have gone so far in space. And that trip took about 3 days to get those astronauts out there. And then we can keep going farther. So this is kind of getting into the domain of uncrewed spacecraft, right? We've sent many probes to other planets, to the sun. Parker Solar Probe is one that I am very interested in, that is taking the closest approach ever to our sun, which is right down there in the middle of our solar system. So we've got the orbits of Mercury, Venus, Earth, Mars, and we can go out even farther. And we get to the gas giants, Jupiter, Saturn, Uranus, and Neptune all the way out here. So our Earth is about 93 million miles away from the sun. Neptune is something like 4 billion miles away from the sun, and sending spacecraft to the outer solar system takes a long time. The New Horizons spacecraft, which was launched back in 2006, it flew by Pluto in 2015. So it took 9 years to get all the way out to Pluto, which is out past Neptune. And it's one of the fastest spacecraft that we've ever sent out into space, and it still took 9 years, and that was just to make a flyby of Pluto. So if we ever wanted to send something to the outer solar system and have it like slow down and actually orbit, it would take a lot longer. The Cassini mission, for example, to Saturn, that took 7 years to get out there, but that was including having to kind of slow down and get into a stable orbit around Saturn. So kind of even sending things in our own solar system with current technologies using rockets that we're all familiar with, that it takes a long time. And so now this kind of looks like the edge of our solar system. Out past Neptune, we've got the Kuiper belt. That's kind of where Pluto lives. It's like another asteroid belt out there. Lots and lots, hundreds of thousands of objects orbiting out there. But that really isn't the extent of our sun's gravity. So there are some different definitions of the edge of our solar system. Some people define it as where the sun's radiation is no longer the dominant form of radiation, and rather radiation from other stars is just as prevalent as any radiation from the sun. So that's one kind of definition. And then another definition is the extent of the sun's gravity, which would make the solar system a whole lot bigger than what we're looking at right now. So if we were to keep going out and look at the extent of the sun's gravity, we can add a sphere. Let's see if I can find it. Solar system. And we're going to be adding objects that are a part of the Oort cloud. Here it is, the Oort sphere. All right, so this grid is representing a radius around our sun where we see objects orbiting all the way out here. So you can't actually even see the orbit lines of the planets anymore from this perspective. But this area, it's called the Oort cloud. It's where comets come from. So this is an area full of icy bodies that sometimes get knocked into the inner solar system. And as they get closer to the sun, they heat up and they sublimate. They just change from a solid to a gas, and they grow these really big long tails. And that's how, this is generally where comets come from. And we are approximately 1 light year away from our sun. So a light year is the distance that light travels in a year, and it's roughly 6 trillion miles or so. So these objects all the way out here, a full light year away, are still in orbit around the sun. So this is kind of the other definition or the other extreme when we're talking about the edge of the solar system. So if I jump us back real quick to here. So this is the kind of scenario one, right? The edge of the solar system that is defined by the sun's radiation. So in this graphic here, we can see the solar system in the middle there, and this blue ball here in the center. And then the heliopause, the heliosphere, this is all areas that are dominated by solar radiation. From the solar wind, and that is radiation and charged particles coming from the sun. And the heliosheath, this kind of marks, or excuse me, the heliopause marks the boundary of this radiation. And so the Voyager spacecraft, those are the spacecraft that are the farthest things that humans have ever sent out into space. They have officially crossed the heliopause. And so they are now in a part of space where the radiation from other stars is about the same as the radiation from the sun. So in some respects, they are in interstellar space already. But if you were to compare it to like the distances to the nearest stars, they're really still very close to home. Voyager 1 is the farther of the two, and these were launched back in 1977, and they've been traveling ever since at about 10 miles per second. So they're going really fast. I think that translates to like 36,000 miles an hour. So they're zooming through space, traveling for over 40 years, and they are around 20 light hours away from the sun, or away from Earth, I should say. So really, they're not even a light day away yet, let alone a light month or a light year. And the nearest star to our solar system is 4 light years away. That star system is called Alpha Centauri. The specific star is called Proxima Centauri. And so if these spacecraft were pointed in the direction of Alpha Centauri, they're not, unfortunately, because their missions were mainly to investigate planets in our solar system. But if they were pointed in that direction, it would still take them another 80,000 years before they would actually reach that star, that closest star. So while they may be in interstellar space, they are still very close to home in the grand scheme of things. And here's another graphic that kind of shows you the other definition of the edge of the solar system, which is the extent of the sun's gravity. We see the position of Voyager about 100 AU, astronomical units away from the sun. This is a logarithmic scale. So the Oort cloud, we get pretty much between 1,000 and 100,000 astronomical units from the sun. This is where these objects are orbiting. Somewhere in here, like around 68,000 astronomical units is about a light year. So the Voyager has not even really come close to leaving the gravitational pull of our sun. So in that sense, it is still very much inside of our solar system, and it will be for a very, very, very long time, like tens of thousands of years. All right, so when we think about sending spacecraft farther than that, There's different ways that we can think about it. The slow, uncrewed spacecraft is what we've just talked about, the Voyagers, right? In tens of thousands of years from now, if humans are still aware of the Voyager spacecraft, they might have some insight into where those spacecraft are, how close they are to any other stars out there. Again, they're not pointed at the Alpha Centauri system, but eventually, stars move as well. So by that time, I believe there's actually another star system called Ross that will be closer than Alpha Centauri. So that's one way to do it. If we were to actually plan for this, then we would have to send a spacecraft which the technology could last for that long. And so right now, we simply don't have that capability to have technology last for tens of thousands of years. So it's really not feasible to send anything with, current rockets, current speeds out into space and expect that generations down the line, tens of thousands of years from now, humans will be able to actually check in with that spacecraft and get data from that spacecraft. So that's pretty unlikely. The next kind of scenario is fast uncrewed spacecraft. And this is the one in particular that I think probably has the most feasibility to it, because there are already some projects that have been proposed to create these types of spacecraft. So I'm going to go into a little bit more detail on one in particular, but I do want to pause and see if there have been any questions so far. Awesome. All right. Let's see all my windows. Okay, so fast uncrewed spacecraft. So these types of spacecraft would have to be very tiny. We're talking like millimeters in size. And this particular one, this is called the Starship, and it was proposed by a company called Breakthrough Starshot, which was founded by Yuri Milner, Stephen Hawking, and Mark Zuckerberg. And they are proposing a fleet of 1,000 super teeny tiny spacecraft that are all kind of kept in one like mothership that is then propelled by a solar sail. So solar sails are really interesting. They are light sail is another term for it. But they're really kind of cool. So out in space, when we send spacecraft to other planets, we actually have to take into account motion changes from radiation from the sun, because that radiation exerts a pressure on spacecraft and can actually change the trajectory. It can even happen with asteroids over very long periods of time. The pressure from that solar radiation can actually change the asteroid's orbit. Not by a ton, because the pressure exerted from solar radiation isn't lot, because it's very spread out. Rate a whole bunch of light on something like this, a solar sail, light sail, then we would be able to use that radiation pressure to accelerate something to close to the speed of light. Because with interstellar travel, it's pretty necessary to get something going fast if we want to see results. Funding doesn't tend to last for hundreds of years or thousands of years. So we do want something that can get there within a human lifetime. So a solar sail like this would have to be really, really big, obviously much bigger than the super teeny tiny spacecraft that it would be propelling. And it would be propelled by a whole bunch of ground-based lasers, an array of a kilometer wide of lasers pointed at the light sail. And so they would need to maintain this focus for a pretty long period of time in order to accelerate the spacecraft to, a significant fraction of the speed of light, like a tenth of the speed of light is pretty, is kind of like the reasonable mark. And so there are obviously some challenges with this type of design. It is extremely expensive. Having the lasers concentrate for such a long period of time to accelerate the spacecraft would also, that might, not the energy required to do that might be too much. The sail itself also is an engineering design challenge. Because you need something that is incredibly thin, but is also strong for, to resist any kind of tearing. And you wouldn't want anything super taut. You'd want something that kind of billows to prevent any kind of tearing. So this particular group of spacecraft, this fleet, the Starship, the idea is to get it traveling at 15 to 20% of the speed of light. And in that case, it would be able to make it to that nearest star system within 20 to 30 years, which is pretty decent. We've had solar system missions that have taken that long. So it is pretty reasonable. Once it is there, it would then take 4 years to get any kind of communication back from that spacecraft because it's 4 light years away. So that communication delay would certainly, limit some of what we could do in interactions with that spacecraft. But this particular one, the target chosen is Proxima Centauri b, which is actually an exoplanet that is orbiting around Proxima Centauri, that closest star. And they chose this particular exoplanet because it is similar to Earth in size, and it's in the habitable zone of that star. Now, Proxima Centauri is a very small to low mass red star. So being in the habitable zone around a star like that is very different from being in the habitable zone around our sun. So, if we're looking for evidence of life or anything like that, it would probably be very different. It would have evolved very differently than life here on Earth simply because of the difference in the stars, our sun compared to this one. Another thing to consider with this particular spacecraft is that it would not be able to decelerate. So it can't go there and then orbit around or hang in the area and then come back. It would have to be a flyby. So similar to the New Horizons spacecraft with Pluto, that mission would have taken so much longer if we were trying to get something to actually orbit around Pluto. So in order to, oh, sorry, I just lost my slide. Okay, there we go. There's just windows popping up everywhere. So in order to send this spacecraft, you wouldn't be able to slow it down. That would just increase the travel times too much. So it would be a flyby, and ideally get as close as possible and just take as many pictures as possible and send it all back. And then it would just continue floating out in space. Any questions? Let me see.
Glenn did have a question in the chat.
Yeah.
So why does the Starship have so many sails? Like, do those use and help maneuver the spacecraft into different directions, or?
Yeah, so the sail would actually be, it would be one sail for all of the tiny spacecraft. And the reason for having so many, I'm honestly not entirely sure. I imagine that having a lot of super teeny tiny spacecraft, they could kind of work together to like network into like a larger spacecraft. So if you think about This is kind of a weird analogy, but the Event Horizon Telescope, the telescope that was used to capture the first picture of a black hole, that telescope was actually an array of well, it wasn't an array, but it was a combination of telescopes all over the world looking at the same target and taking pictures, and then taking all those pictures and putting them together to make a more detailed picture. Because in order to resolve an image of an object that is that far away, you would need an Earth-sized telescope, which is impossible with current technologies. So they simulated one using a whole bunch of telescopes around the Earth. So I would think that maybe having lots and lots of these tiny spacecraft would do something like that, where it would simulate a much bigger one. But it's easier to get the really tiny ones moving at a fraction of the speed of light than it is to get something more massive. But the sail, there would be one sail actually being used to propel all of those tiny spacecraft, if that makes sense. But that's a really good question. Any others? All right, cool. We can move on. So that's a little bit of an insight into these fast uncrewed ships. And as I mentioned, there are a lot of proof of concepts and ideas behind this particular type of plan. So I think that this is the most feasible at this point in time. So the next one is pretty wild. We can move into slow crewed missions. So these types of missions are all extremely hypothetical. We do not have any technology that could make any of these happen soon, maybe down the line. But these types of missions, they're pretty wild, and you've probably seen them in a lot of sci-fi movies. But the first one is like what's called a generation ship. So it would be a ship where people would live on it, but then have children, and then those children would have children in order to last, maybe thousands, multiple generations, hundreds to thousands of years to make it to another star system. So this is not really feasible for a number of reasons. I mean, the psychological effects of living on board a ship your entire life and raising other humans on it, and then this continuing being educated on the ship as well. You'd need teachers, you would need an insane amount of resources, right? Like being able to support people for their entire lives would just be, I mean, incredible to think about. But we're very far from anything like that, but that is kind of one of the ideas being floated around. This next one I've seen a ton in sci-fi movies, which is suspended animation. So basically, you would send humans up, as you would to go to the moon, but then they would, either freeze, like a cryo freezing situation or something similar, where they would just kind of go to sleep or be in this like suspended, almost hibernation state until they got to the destination. And the idea here is that resource, you wouldn't have to really worry about resources too much, because they're not going to be consuming any resources while they're in this like hibernation state. And this one feels very out there, but I think that once like the technology is solid, this one might be the most feasible of all of these. So yeah, I think the Alien, 2001: A Space Odyssey, Event Horizon, if you like horror space movies, they've all done this kind of suspended animation. And it also works really well in films, because then they don't have to worry about like reconciling all of the equipment and interpersonal relationships and psychological effects that happen to people on super long space flights. And that's actually kind of one of the areas that is challenging about getting humans to Mars is thinking about how a trip like that would last, between 6 and 9 months. If we were sending humans, we would make sure that it was 6 months. But even that long can have a lot of psychological effects on the people on board. So the whole thing is pretty interesting. And then the last and maybe most out there of these three are frozen embryos. So if you could somehow, which, that's possible already on Earth, but then, sending those out into space, you can't just send them out and then, they grow up and they're fine, right? So you would need to create like an artificial uterus. You would need artificial intelligence to raise the babies, the children, the humans. And then you would need like AI to educate them as well. And that just comes with all kinds of questions and ethics questions and all kinds of stuff like that. So it's really interesting to think about, but all three of these methods are pretty out there and definitely far into the future, I would say. All right, and then the kind of last option here are fast crewed missions. So this would be getting people into interstellar space to other solar systems within a human lifetime. So people that could live to tell the tale, basically. And this is where all kinds of really weird physics comes in. It's not really being able to propel something very massive at a close to the fraction of the speed of light is not possible right now with current technologies. There are different ideas about how to do that, but people and the resources that they would need is just simply too much to be able to get anything going that fast. That's why the fast uncrewed spacecraft are so teeny tiny. So in this kind of hypothetical situation where we have people that could be propelled to a significant fraction of the speed of light, there are some weird things that happen, right? Because as you move closer to the speed of light, physics, you start to experience all the effects of special relativity, which basically means the faster you are going, the closer to the speed of light you're going, the slower time goes by from an outside observer. So if I was observing something moving at the speed of light or close to the speed of light, a clock, we'll say, to me, that clock will look like it is moving much slower than my clock in my own reference frame. Now, from the clock's perspective, time is moving as normal. And to them, it would appear that my clock is actually moving slow. And so what ends up happening in these types of hypothetical missions is that as somebody is going close to the speed of light, long distances, time for them passes like normal, but time if they were to come back, there would be a longer period of elapsed time on Earth. It's very, very strange to think about. And this is one effect of special relativity. You also kind of get weird things like length contraction, and the way things look would be very, very distorted because of the Doppler effect, which I can actually show you a little bit of what this looks like. So this is a free game that was created at MIT that is meant to simulate what it would be like traveling at a speed close to the speed of light. And it's called a slower speed of light because instead of you moving closer to the speed of light, it's actually taking the speed of light and making it slower to kind of, make it more relatable. So this is just a video of me playing it ages ago, and I won't show you everything in it. But I'll kind of scrub through. So you get these little orbs, and with each orb, the speed of light gets slower. And so eventually, once you collect enough of them, you start to see the effects of special relativity as you move through this game. So color distortions happen as you're moving toward an object, wavelengths of light kind of squish together, and so you see more blues. As you move away from objects, you tend to get lengthening of these wavelengths of light, so you see more toward the red side of the spectrum. And so this game does a really cool job of showing you what it would be like to travel at close to the speed of light. You can also see some effects of like length contraction and things like that as well. And it's just kind of it's cool art. It was a fun experience, but that's free to download. I think you could just look that up and you'll be able to find it somewhere. It's called The Slower Speed of Light. So anyways, those types of relativistic effects on humans, that has never really been studied so far. We don't know what would happen to a human if they were moving at speeds close to the speed of light. And so there's a lot of questions there as well. All right, so then kind of the next question here is like, all right, well, what is being proposed as propulsion? Because rockets, current rockets, they are really good at sending spacecraft into space to look at our solar system. They are relatively cheap compared to all of the options that we've already talked about. There's not enough money in the world really right now to support any of them, except for maybe the fast uncrewed spacecraft. But there are a lot of ideas, and some of them are out there, some of them are more feasible than others. So light sails, we've kind of already talked about those, but using lasers to power a sail and accelerate something at close to the speed of light. Nuclear fission, this is actually one of the first proposed ideas for getting something close to the speed of light, is literally just setting off a whole bunch of nuclear bombs behind a spacecraft. And we would need about 200 times more of our global arsenal to power a spacecraft and get it to 1/10 of the speed of light. So, that would require a lot of money, a lot of resources, a lot of trust. Building nuclear weapons and that amount doesn't sound great, but, if we're facing human extinction, maybe it is something worth it. So that is one idea. Nuclear fusion, which is the process that keeps the sun and stars going, is another option, and being able to harness that and have it in a contained, controlled area that would provide a lot of energy. Then we kind of get into these more mysterious areas, like using antimatter, for example. When regular matter and antimatter collide, they annihilate and they produce a ton of energy. And so that would be super efficient if there was a way to kind of harness and isolate antimatter, and then create some kind of mechanism to control these collisions. That would be a very energy efficient way to propel something to close to the speed of light. But we currently really don't have that kind of technology. If we look at particle accelerators, scientists are able to capture and isolate antimatter particles, but that requires a whole bunch of electromagnetism and just a lot of resources that we're not really sure how that would work on a spacecraft. The next one is really fun. It's an artificial black hole. So if we were to take the mass of about like 2 Empire State Buildings and squish that down into the size of a proton, that would create a black hole that would eventually, over the course of a few years, radiate energy and Hawking radiation. And so this radiation would be able to propel a spacecraft as well. But the energy required to create this black hole that would probably come from lasers would be more than the black hole itself. So lots of questions there. And then the last one is extremely wild. it's basically, you know, just as wild as thinking about like a wormhole. It's called an Alcubierre drive, and something like that would actually warp the fabric of space-time to create like negative gravity in front, and you know, normal gravity behind that would kind of push it through, like almost like riding a wave of the fabric of space-time. So there's all kinds of really fascinating like thought experiments and hypotheticals, about ways to actually propel something to the speed of light. This is an example of a spacecraft that was proposed back in the 1960s. It's an example of a fusion controlled spacecraft. So basically it would take hydrogen atoms from the interstellar medium, and kind of siphon them into this controlled environment, where very high pressure environment where they could fuse and create energy the way that it happens inside of the sun. But more research has shown that there aren't actually that many hydrogen atoms floating in interstellar space. So something like this probably would not work. This is the warping of the fabric of space-time that would be required for an Alcubierre drive. And honestly, I don't really fully understand how it works myself, beyond just like a basic definition. So it's worth some more deep dives for sure, because it's a cool thing to think about. And then, so all of this kind of feels really unrealistic, very out there. And so like, what is the current state of human spaceflight? Where are we now? What can we do? So we have never gone past the moon, but we are trying to get humans back to the moon and eventually onto Mars. This is all much more feasible and probably within our lifetimes. This is the Artemis program. And in just, I think about a month or two, well, we'll see what happens, because it's been delayed like a million times. So we'll see what happens. But the first part of the Artemis program is set to happen sometime this June. So it'll be the very first official launch of the Space Launch System, which is the rocket, the most powerful rocket ever built, to send the uncrewed spacecraft Artemis 1 into space. And this will be like kind of the first real test of the Space Launch System. And so that's really exciting. That's the first step in the Artemis program. Artemis 2 will be a crewed mission that will send humans to the moon, but not to land on it, but just to kind of take a trip around the moon. And then the third mission, Artemis 3, will be the mission sending people to the surface of the moon. And the goal is to get the first woman and the next man to the surface of the moon by 2025, which seems really soon. So we'll see what happens with that, but that would be awesome. And they are planning to head to the lunar South Pole, which is an area that has been shrouded in darkness pretty much for billions of years in craters around the South Pole. And some of these, at the bottom of a lot of these craters, are some of the coldest places in the whole solar system, because sunlight just doesn't get into them at all. And there's a lot of water ice at the lunar South Pole, so it could be a good place for a potential lunar base, which is another part or objective of the Artemis program, is to kind of set up a permanent outpost on the moon, or at least a space station around the moon, similar to the International Space Station, that would kind of be like a rest stop for humans to eventually go to Mars, because it's much easier to launch something from the moon than it is from the Earth, just, you know, because it has so much less gravity, that it would be ideal to launch humans to the moon, have them kind of regroup there, and then launch to Mars from the moon. So that's the lunar gateway that they are considering, which would be really cool. So this is just a diagram of the Space Launch System, and exactly what it's made of. The command module, or the equivalent of the command module, is the Orion spacecraft, which can carry 4 astronauts. So if they're going to send humans to Mars, hopefully they will get something bigger than the Orion spacecraft, because it can hold 4 astronauts. It's not very big at all, but it could get tight on the way there. And I'm glad that you mentioned the radiation, because that's certainly something that folks are considering for that long trip, because it'll be unlike anything that astronauts have experienced before. Being on the International Space Station, you're still so close to the Earth that you're within Earth's protective magnetic field. And so even though you are getting more radiation than you would on the surface of the Earth, you're still pretty well protected. And with the moon, a lot the missions, they're generally pretty short. So you're definitely exposed to more there, but at least you're still pretty close to the Earth. And going beyond that, there would need to be some serious innovation to figure out how to properly shield folks from radiation, astronauts. And even on the surface of Mars, there's very little atmosphere on Mars and no magnetic field. So astronauts making it to the surface of Mars would need to, build shelters that would either protect them from the radiation, or honestly look underground in caves. That would provide a lot of radiation protection. But yes, they would be fried.
I've heard that there are volcanic tubes, and maybe the tubes could be used as caves to protect people.
Yeah, I've read about that as well. There are so many volcanoes on Mars that are, no longer active. They are all extinct, but they have these, remaining volcanic tubes that certainly could function as shelter and really protect folks from radiation. This is an artist illustration of what a lunar gateway might look like. So it's pretty kind of similar to the International Space Station, a bit smaller, but it would also be an international effort, and it would be assembled modularly, similar to the International Space Station as well. And here are some of the astronauts from Team Artemis. There's a whole bunch that are being considered for the trip, but the actual astronauts chosen for that Artemis 3 mission has not been decided just yet. But astronaut Stephanie Wilson, she's actually from Boston, and I think she's local, so I'm rooting for her. She's the one all the way on the right.
Will they bring do you know what the time frame is for the first module of the gateway? How soon that will the gateway be established before anyone touches down on the surface of the moon in the Artemis program?
I think it's planned for after Artemis 3. So it would the time scale is much longer, and I would put it more toward the end of this decade. Then if everything goes as planned and astronauts are able to get there by 2025, then it would be maybe toward the end of the decade. Any other questions before we wrap up? Sounds like we're good.